Thank you everyone for attending. This is the international seminar series of the Masters in Civil Engineering, Javeriana University. We have Professor Longinow from the Illinois Institute of Technology. He is also a structural consultant for 20 years in the city of Chicago. And kindly today he's going to share with us the experience of the World Trade Center in 1993. So Professor Longinow, welcome, and welcome also to the people online and to the students that are here. Thanks so much for your time, and the room is yours.
Okay, thank you very much. Well, I'll be talking about internal explosions. So internal blast, I'll talk about that a little bit, and then we'll get to the World Trade Center. I'd like to introduce what internal explosions are. So you can have a detonation of high explosive. You could have ignitions of mixtures of flammable gas inside of a building. Accidental ignition of mixture of flammable gas produced by gas leakage. All those can produce explosions internally. Okay. Characteristics. In terms of characteristics of the resultant blast, the main distinction to be drawn is that between the detonation of high explosive and the deflagration, which is a more or less rapid explosion produced by a gaseous mixtures or fine solid suspension. The first, the detonation, is independent of atmospheric oxygen and leads to a very rapid production of large quantities of very high temperature gas in a very small space. That's a detonation. This gives initially at the source of the explosion a very high but very localized pressure rise, which leads to a shock wave expanding away from the source to speeds greater than, speeds like the sound, like speed of sound, which is approximately 1,000 meters per second. As the wave expands, its peak pressure falls rapidly off with distance, and behind the peak there's a rather less rapid fall in pressure to somewhat less than atmospheric pressure. The effective duration of the oil pressure becoming longer as the distance from the source increases, and the reflections of the wave by obstacles may either amplify or attenuate the basic pressure. Okay, so this shows a variation of pressure from an explosion, detonation, outside of a building, external to a building. As you can see, the pressure decreases with distance. We have the oil pressure, distance, and then at this point, at the last point, we have a positive phase duration, negative phase duration. This is a characteristic shock emanating from the source. Okay, but when the explosion takes place inside of a building, there will be reflections, even when some of the floors or walls have been blown apart. This will tend to prolong the duration of the pressure above atmospheric throughout the space. In addition to shock loads, there will be also pressure loads. The gaseous products inside the building will accumulate and the temperature within the structure will rise. This will form blast pressures whose magnitude is generally less than that of the shock pressure, but whose duration is significantly greater. So for example, this is a depiction of a point source explosion inside of an enclosure. So you see the ceiling, you see the walls, the floor, you can see an opening at the left side. Explosion takes place in the lower left-hand corner, and you see reflections from the walls, as long as they are not blown apart. You see. Okay, so this is kind of an approximate depiction of what can happen inside of a building. All right, you go to, and this shows how the loading is going to be on the walls, ceilings, etc. You see, you have a shock loading, which lasts a short time, and then the gaseous product loading lasts a lot longer because of the reflections of the product. Okay, so much for this basic stuff. But you see, the detonations inside of buildings are rare. very rare. This could be, they can be produced by processes that can result in detonations in manufacture, for example. What comes to mind are detonations from mail packages containing explosive or letter bombs. There's also the possibility of someone leaving a briefcase or a backpack containing explosives. So those could become detonations inside of buildings. Now you may recall that the London Underground bombing, which took place in July 7, 2005, and in Madrid train bombing, which took place in March 11, 2004, can be considered as internal explosions, where the terrorists brought on board backpacks containing explosives. These were relatively small bombs. Those in London weighed about 10 pounds each. Those in Madrid about 22 pounds each. The size is not important. It's what the type of the explosive that's important. Now, these explosives probably consisted of plastic explosives, which are available on the black market. Had they contained Semtex, a military explosive, casualties would have been much greater. Okay, now let me briefly introduce one small subject, internal explosion produced by aerial bombs. This is a World War II experience. What I'm going to show you here is a report produced by an engineer of an explosion which took place in London, England. You will notice on the next page it took place in 1943, May 1943. So what happened here is a bomb, a German bomb weighing 550 pounds, hit the roof of this building, broke the roof, broke the second floor, first floor, and exploded in the basement. So this picture shows the shock waves emanating from the explosion. It shows the damage produced by the blast, both in this picture and in the plan view. See, this was a very long sheet, so I had to break it into two parts. So this part shows the damage to the floor systems. The cracks are shown over here. And over on the right side, you see a picture of what happened to slab and beams inside that building. Now, this whole report here was prepared by an engineer in England in 1943, and the pictures are shown on the left side, description of damage. The building is described, damage is described, and this is done very well. Now, keep in mind that this took place in 1943. Cameras were not available at that time like we have now. So you see, this was done by an engineer who very carefully went out to the site, inspected the damage, made a lot of sketches, drew things up by hand, and did a very good job. It impressed me very much what can be done without a camera. This was a very well done report, one-page report, and it shows you an internal explosion produced by an aerial bomb. Okay, now we get to the main topic of this presentation, the internal explosion inside the World Trade Center, which took place in February 26, 1993. It's a long time ago now, but still it was an important event. Now here, this picture shows the World Trade Center, the two towers, which no longer exist, as you know. The Vista Hotel is shown on the lower right, and the Vista Hotel was destroyed also, but it plays a part in our discussion here. So, just let me kind of briefly tell you what happened here. So on Friday, February 26, 1993, I can't quite see what this says here. Let me remove this. Whoops. Okay, so about 1,800 pounds of explosives ripped through the 6 sub-basements floors that house operations such as maintenance offices, primary and secondary power plants, fire safety, communication, refrigeration systems, and the public parking, tenant and the public parking. So the man drove up this van containing these explosives, left it there and detonated it. Okay. Whoops. For some reason, I am unable to move. Next. So the blast created an internal underground crater, which involved 5 stories of the basement and covered about 16,000 square feet of damage. You see, the top of the crater was at the plaza level, where approximately a 10-foot by 10-foot section of the floor slab was cracked and deflected upward. Now, I sketched here what that looked like. You see, the explosion took place at the B2 level. You can see the explosion, you can see B2 level. So it cracked the slabs above the explosion, also broke the slab to the shopping center, and actually broke the slab at this level at the Vista Hotel. There were no slabs at the B3 and B4 and B5 levels. No, B3 there was a slab. B4 and B5 there was no slab. So the debris from the explosion fell down into the area below where the AEC equipment was there. I'd like you to note there's something called the path tube shown on the right-hand corner way at the bottom there. That's a subway system. So even that was affected by the blast. Okay, so what you're looking at basically is kind of a plan view of the basements of Tower 1 and the explosion and what it did to the various floor slabs. So on the next level, the concourse. So let me go back here. So this is the concourse. So we are talking about the concourse. So on the concourse level, a plaster on glass ceiling collapsed in the lobby of the Vista Hotel. Directly below the collapsed ceiling, there was a hole in the slab of approximately 18 by 22 feet, which is about 396 square feet, made by the explosion below. On the B1 level, let me show you the B1 level that we're here. There was a hole about 50 by 80 feet. So that hole here, 50 by 80 feet, 4,000 square feet, where the floor slab on that level collapsed. Now this is the same picture I'm showing you again, just so you get an idea of what happened. So the blast, the dashed line shows where the effect of the blast was. The largest floor slab collapse occurred on the B2 level, where the collapse area measured about 130 feet by 130 feet. This level is where the van containing the explosive was parked. So you see the B2 level, right? Let's go back to the B2 level. So at the B2 level is where the van containing the explosive was parked, okay? Okay, and this was...
Professor Longinow, do you mind if I explain that area in terms of meters? In here, we are not that accustomed to a foot.
Sure,
do you mind if I explain that a little?
Yes, please. You want to see the slides or no?
Yes, please. You can go back to the sketch. Professor Longinow explains that at level B2, the hole was 40 meters by 40 meters because of the explosion. That's it. Thank you, Professor.
And this is where the van was parked, the one which exploded. Okay, so we go next to here. Okay, because there were no floor slabs at B3 and B4 level, there were no floors. Oops, sorry, there were no floor slabs at B3 and B4 level. There were no floor slabs, so the debris fell down onto the AC equipment. Okay. Okay, this again shows the same thing we just talked about. You see the Vista Hotel. You see level B2 where the van was parked, and that's the explosion where it took place. And then you see B3 and B4 levels had no floor slabs. So basically 2 floor slabs were damaged. And even into the Vista Hotel, the floor was damaged. So this was a big explosion. And you can see the 2 towers and so on. So let's go on. So what was used? The explosive used was ammonium nitrate fuel oil. And ammonia is an essential ingredient in nearly all commercial explosives in this country. It's more than 1 billion pounds of these mixtures, commonly referred to as Anatol, are consumed each year in the States. They account for approximately 80% of the domestic commercial market, explosive market. Anatol products have found extensive use in a variety of blasting operations. Surface mining, for example, metal mining, quarrying, construction. Their popularity has increased because of economy and convenience. The most widely used Anatol product is an oxygen-balanced, free-flowing mixture of about 94% ammonium nitrate, prills, and 6% number 2 diesel fuel oil. And of course, you need to have blasting caps to set the whole thing off. You need to know how to mix it properly. And apparently this particular person who did that was quite adept at doing what needs to be done to create a good explosion. Other damage in the basement area. Concrete block walls on the B1 and B2 levels were severely damaged. Damaged walls included those enclosing rooms, stairways, elevator shafts. The damaged walls were as far away as 550 feet from the blast area. Okay, I can't tell you how many meters that is, but
that's about 180 meters. So 180 meters away from the explosion, the walls were destroyed.
Yes, many metal doors were bent and distorted, and some doors were knocked out of their frames. Approximately 200 cars parked in areas adjacent to the crater were heavily damaged. Cars closest to the explosion were rolled over, ripped apart, and dented on surfaces, and many of them burned. Cars more than 100 feet away from the edge of the crater were also dented. The force of the explosion even cracked tunnel walls enclosing the fast tracks at the subway at the B6 level. Okay. I made some calculations to show what the pressures were at different distances from the explosion. So you see, at 10 feet away from the explosion, the pressure was incident 1,300 pounds per square inch. And then 100 feet, etc., etc. At 550 feet was the 1 pound per square inch. Well, 1 pound per square inch is still a high intensive explosion. Okay, this may not be too important to you, but still it gives you an idea what the pressures were inside the basement. The demolition contractor removed approximately 4,800 tons of debris. The repair crew attached 180 braces to damaged columns. 1,042 people were injured, mostly due to smoke inhalation. There were also 15 persons who suffered blast damage, blast injuries. Six people were fatalities. Okay, the next 4 slides show the crater area, blown out slabs, damaged columns, etc. Temporary column braces. Okay, now this is kind of an important slide. You see what happened here. You can see that this. I have something that obstructing my view over here, but that's okay. What you see is that here are the slabs, missing slabs. So you see, you design a column to be between 2 floor slabs. The floor slabs provide resistance, so the column doesn't buckle. But here, the slabs were gone, so the whole column over here was like 40 feet long now. Well, before that, there was maybe 15 to 20 feet long. So the columns were in danger of buckling after the explosion. Okay, so that's kind of important. Now, see, now what you see are the steel bracing. Those were put in after to make sure that the building doesn't buckle, collapse. Okay. Now let's go further. Okay, so here, if you were to step into this, if you were an engineer to step into this building and you were told to try to fix it, or tell people how to fix it, what to do. This is what you would see, right? Okay, what you see here are the column capitals, right? Column capitals at several levels. They're gone. The slabs are gone. Now, what the engineers did, see, it took the engineers. City of New York hired about maybe 6 different or 8 different engineering firms. WJE, the firm I worked for, was also hired. Our office in Princeton, New Jersey, took the job, so our office directly here in Northbrook wasn't involved. So I was involved only on just at the edge of it. So I knew what was going on. I saw what was going on. So you see what we did. We brought in. It took more than a week to do that, probably more 2 weeks. And we were worried about the columns buckling, something happening. So you see the walkways over here at the top. Those are walkways which were put in to walk around, so we could go from column to column, and the workers could brace those columns. Okay, let's go next to another slide. Okay, this is another view of the same thing. You see column capitals. Okay, you can see the braces which are put in. You see the workers welding the braces to the columns so the columns would not buckle. Okay, now we can go further here. Okay, here's another view of the whole. You can see how large the area was. How many slabs collapsed, and how much work had to be done to put in walkways, wooden walkways, and metal walkways, and brace the columns and weld it to make sure that it took weeks, several weeks to do that. Many workmen were involved. Supply companies were involved. You see. Okay, other damage. The next 4 slides show damage to areas away from the collapsed floor slabs. You will note cracked floor slab in the vicinity of a column. You will note columns that lost their fireproofing. And you'll note that dented pushed cars in the background. So here's a column. You see the column capitals. And this column is a steel column encased in concrete. Now down below, you see the cracked slab that the explosion took place underneath. So it kind of lifted up that slab. Now you know that when you design floor slab, you design them for vertical loading. Right? So we put reinforcement at the bottom level. If an explosion occurs below and the loading is from below on the slab, that reinforcement doesn't help very much, and the slab breaks much quicker, more easily, I should say. Okay. Here's another column where the part of the concrete fireproofing has been blown off. I'd like you to take a note of the cars which are dented cars. On both sides, you see dented cars pushed aside and dented. Here is a column which lost all of its fireproofing. And you see that the bent slab over here, steel plate. We didn't know what happened, how it could bend like that. But you can see over here, it's the same column showing that dented slab. You see, it took a lot of pressure to blow off that fireproofing. Conclusions. Okay, first of all, the same quantity of explosive, if exploded next to this building, are not likely to have produced as much damage as when exploded inside. Confinement increases the effectiveness of an explosion, as I mentioned very early in this talk. Several of the floors were loaded from below, as I mentioned. In this manner, they fail easily because slabs are reinforced for gravity loads and have only minimal resistance against an upward load. Right? Significant portions failed on several floors and thus removes lateral support to the column, as you saw earlier. However, the building did not appear to experience any local instability. See, structures are very good. Structures share loads. If a member gets removed, the other members will try to share the load. Post-mortem reports indicate that numerous cars were set on fire. However, the fire problem in the garage was minimal. The collapsed slabs tended to minimize the fire problem because many cars were dumped into the pit below. Casualties. The smoke, which caused 1,000 minor injuries, was caused by numerous burning cars, mostly on the B2 level. 6 building occupants died immediately from injuries sustained during the explosion. 4 of the victims were Port Authority employees who were in an employee lounge on B2 level, Tower 1. The room was separated from the explosion area by a concrete block wall, which was destroyed by the blast. The 5th victim was returning to his car in the sub-level garage when the explosion occurred. The 6th victim was last seen in the food commissary on the B1 level shortly before the explosion occurred. Totally, in all, 1,042 people were injured, including 15 who suffered blast-related traumatic injuries, such as being cut by broken glass, for example. Okay, that's the end of my talk on the World Trade Center. So I was asked to tell you something about the project we had here not long ago. I teach a course which is called Engineering Aspects in Homeland Security. And what I do there, as Federico can tell you, is that I break up the class into groups, and each group does a project of some sort, and the project deals with some aspect of terrorism. So about a year ago or so, a little bit more than a year ago, 3 students picked a topic which involved you recall that recently we had these cars running into groups of people, killing them. So they did a project on that, and they did a very good job. They collected the data on all the events which occurred in Europe, mostly in Europe, the casualty data, damage data, who the people were, who did the driving of the truck. So that was well documented, and they also came up with ideas of how to prevent something like this from happening. So they put together ideas such as barriers of various types, which can be put up to prevent this happening, which would not be too expensive, but could be put up fairly quickly. They also suggested what can be done to trucks to prevent a truck. For example, if you can put some kind of an instrument in the truck, which could be stopped, which would allow the truck to be stopped remotely. You see, so if a truck is stolen, for example, and there is a provision in the truck which could prevent the truck from moving further, that would be one way to stop casualties. So anyhow, it was a very nice project. I thought it was a good job. The students wrote a paper on that. The paper was published in the AAC journal, and it was well received. It was well done. So you might want to read that paper. I'd be glad to provide you with a copy of that, should you want to have it. So I wish I could answer some questions if I can. I don't know if I can do that, but I appreciate the opportunity to
let me ask everyone. Does anyone have a question online, or do we have questions about the bombings that we can transfer to Dr. Longinow? Maybe he can answer anything, a question. Professor, I have a question. Can you go back to the picture where they are welding the bracing elements on the column that is about to buckle?
Okay, okay. Let me. Here's okay, this is one.
Probably
This is
the one before that, where we can see the people working on the column. There, right there.
right.
How many hours or how many minutes after the explosion did those people welded those bracings to avoid the buckling of the column?
Well, you see, it took a long time. I should say a long time. It was a very nervous time. It took at least probably a week to order the material, to bring in the wood to build the walkways, so we could get from column to column. It took also several days to bring in the steel and to carry it to the various columns. So it took a while. You know, I can't tell you exactly how many days, but it took over a week, possibly 2 weeks before this was finished. I just want to go back a little bit. Let me go back a little bit further because it just shows you that, you see, 100 braces were attached to the columns.
Oh yes, Jesus Christ, so that's terrible. Well, it was also a miracle it didn't collapse by its own weight.
Well, it could have collapsed, but you see, that's what I said. When it comes to structures are very good at sharing loads. And this building was well designed, so it shared loads.
That's
So
right.
but many columns were damaged. That's a lot of braces.
All right. So no questions on the room. Okay, that's it, Professor Longinow. Thank you very much for your time. Right now we are about 20 people in the room and some other 5 online. Thanks so much for your time. I will share the paper you gave me with the students, and also at the end of the presentation, I'm going to show them the video that I collected on the website, with your permission, just to let them know how the moment of the explosion was and like the casualties and the very moment of the explosion.
Okay, very good. Good.
All right.
Thank you for
Thank you very much, Professor. Have a good day.
Bye.